You know, you see it in sci-fi sometimes, but we're talking about technology that's actually here right now. The idea of making pure, safe drinking water just straight from the air. It sounds almost too good to be true.
It really does, but it's grounded in, well, pretty basic science. Just engineered very cleverly.
So that's what this deep dive is all about. We want to understand the actual science behind atmospheric water generation, or AWG. We're looking specifically at systems like the air fountain, kind of peeling back the layers on how they take humidity from the air, something that's all around us.
And often totally ignored.
Exactly. And turn it into drinking water. Our mission today is to really unpack how it works, the physics, the filtering, the whole process.
Right. And just to set the stage, AWG isn't pulling water out of thin air magically. Air, always has some moisture in it. Always. Even in dry places. Think about dew on the grass in the morning or condensation on a cold glass on a summer day.
Okay, yeah. Familiar stuff.
That's the natural process. What these systems, like the air fountain, do is basically take that natural condensation and put it on steroids. They amplify it. They engineer the conditions to capture air, force the condensation, purify the resulting water, and then store it safely. It's a closed loop.
Okay, let's break that down then. Section 1, the core science. Capturing that air and condensing the water. First step must be just getting the air into the unit, right?
That's step 1, capturing humidity. You've got these pretty advanced intake fans pulling in the ambient air. But crucially, before anything else happens, that air hits high-efficiency filters. You can't have dust, pollen, general gunk getting into the works.
Right, it makes sense. That cleans the air first.
Exactly. It protects the water quality downstream, but also the delicate machinery inside, like the cooling coils.
Okay, and this is where it gets interesting for me. The sources claim these systems can work even when it's not super humid, like down to maybe 35% humidity. That seems ambitious.
It is ambitious. And that 35% figure, well, that's really where the modern engineering shines. Older AWG tech often needed much higher humidity, maybe 60–70% to be practical.
So what's the trick? How do they pull water out when the air is relatively dry?
It's about efficiency, maximizing the surface area where condensation can happen and making the cooling process incredibly effective. They use advanced materials for the cooling coils, really intricate designs. Think of it like maximizing the coldness and the space for water vapor to hit that cold surface.
So the goal is to reach the dew point really efficiently.
Precisely. The dew point is that magic temperature where the water vapor in the air says, okay, I've had enough of being a gas, and turns into liquid water.
Which brings us to step 2, cooling and condensation. The air is clean, it's inside, now we make it cold.
This is the heart of the process. Warm, moist air flows over these intensely cold coils or plates inside the unit.
And how do they make them cold? Is it like a fridge?
It can be, yeah. The sources mention 2 main methods. One is compressor-based cooling, which works, very much like your refrigerator or an air conditioner. The other is thermoelectric cooling, using something called the Peltier effect. These are often quieter, smaller, maybe better for like countertop units.
Okay, but I'm guessing there's a performance difference?
Generally, yes. Compressor systems, while maybe a bit noisier and bulkier, tend to be more powerful. They can usually extract more water, especially if the humidity isn't super high. They're often more energy efficient in terms of liters produced per watt of electricity used when you need higher volume.
So the choice of cooling tech affects output, noise, energy use, lots of trade-offs.
Definitely. But either way, you get these tiny water droplets forming on the cold surfaces, pure H2O, essentially.
And these droplets then just drip down.
Yeah, they coalesce and flow via gravity into a collection chamber or tank.
Okay, so we've got water, but you mentioned it's basically pure distilled H2O at this point. Is that actually good to drink?
Ah, good question. It's clean, yes, but maybe not ideal. Which leads us straight into section 2, multi-stage purification and storage.
Because pure isn't the same as healthy or tasty.
Exactly. The water after condensation is very clean, but it lacks minerals, and distilled water can taste a bit flat. Plus, you want multiple safety barriers.
So what are these stages? Let's walk through them.
Okay, step 3 is the multi-stage purification. Usually 4 key stages mentioned. First up, sediment filtration.
Like a final sweep for tiny particles?
Precisely. Catching anything microscopic that might have somehow gotten through the air filters or formed during condensation, just making sure.
Then stage 2.
Activated carbon filtration. This is really important for taste and odor. Think about the air in your house. It might have VOCs, volatile organic compounds from, cleaning supplies, furniture, cooking.
Stuff you don't want to taste in your water.
Definitely not. Activated carbon is amazing at absorbing those compounds, along with things like chlorine if it were municipal water. But here it's mostly about those airborne organic traces and ensuring a really neutral, clean taste.
Okay. Stage 3 sounds serious. UV sterilization.
Yep. This is the microbial kill step. A UV light lamp exposes the water to ultraviolet radiation. It doesn't add chemicals, but it effectively neutralizes bacteria, viruses, cysts, any microorganisms that could potentially be harmful. It's a safety guarantee.
Like an invisible barrier.
A very effective one. And then finally, stage 4, which might surprise some people, a mineralization cartridge.
Ah, so adding stuff back into the pure water.
Yes, because as we said, pure distilled water isn't always best. It tastes flat and it's slightly acidic. This slight acidity means it can be corrosive over time.
Corrosive to what?
To the storage tank, the pipes, the dispenser mechanism inside the machine itself. Also, our bodies generally prefer water with some essential minerals, so this cartridge slowly releases small amounts of things like calcium and magnesium back into the water.
So it improves the taste, makes it healthier, and protects the machine.
Correct. It balances the pH, making it neutral or slightly alkaline, and gives it that crisp, refreshing taste you expect from good mineral water.
That's clever. Okay, so now we have clean, safe, mineralized water. Where does it go?
Step 4. Storage and dispensing. The purified water goes into a holding tank. Critically, this tank is sealed and made from food-grade materials, stainless steel, or BPA-free plastic to prevent any recontamination.
It just sits there.
Not usually in the better systems. The sources mention continuous circulation and often another UV sterilization loop within the tank itself. This keeps the water fresh and safe, 247, preventing any stagnation.
And then you just get water from a tap on the unit.
Pretty much. And some of the more advanced models even have built-in cooling or heating elements so you can get chilled water or near boiling water on demand.
Okay, the whole process makes sense now, from air to purified, ready to drink water. But let's talk practicality. Section 3, climate, output, and that big one, environmental impact. Does it really work everywhere?
Ah, the rubber meets the road part. Okay, the biggest factors determining how much water you get are, unsurprisingly, humidity and temperature. Warm, moist air is best.
So like coastal Florida versus Arizona, big difference.
Huge difference. In really humid, warm places, like maybe tropical or coastal areas, these units can be quite productive.
Yeah.
You might see figures like 20, maybe even 30 liters per day for a decent-sized home unit.
That's a lot of water, more than enough for a family.
Easily. Now, in more moderate climates, think average humidity, average temperatures, you're looking more in the range of, say, 10 to 15 liters per day.
Which is still pretty good, enough for drinking, cooking.
Absolutely. And this is where that ability to work down to 35% humidity becomes really key. It makes the technology viable in a much wider range of locations, not just swamps. Even in relatively dry, like semi-arid areas, you might still get enough for essential drinking needs each day.
Okay, but what about the energy cost? Pulling water from less humid air, running compressors or thermoelectric coolers? That must use a fair bit of electricity, doesn't it?
It does. That's the main input, the main operating cost. You have to power the fans, the cooling system, the UV lamp, the pump. The energy draw is often compared to running maybe a small efficient refrigerator continuously, or perhaps a dedicated dehumidifier. It's not insignificant.
So how does the cost per liter stack up against just turning on the tap for municipal water or buying bottled water?
That's the crucial calculation for a potential user.
Yeah.
If you live somewhere with really cheap, high-quality municipal water, the electricity cost might make the AWG water slightly more expensive per liter, especially factoring in the unit's purchase price.
But
there are big exceptions. 1, if your municipal water is expensive or the quality is poor. 2, if you rely heavily on bottled water, which is incredibly expensive and generates a ton of plastic waste. 3, if you're off-grid or in an area with unreliable water supply.
So the value isn't just cost per liter, it's also independence, reliability, and quality control.
Exactly. Knowing your water is pure, knowing it's available even if the municipal pipes break, that has significant value for many people.
And this leads to the environmental angle, right? This seems like a big selling point.
It's potentially huge. Think about it. You're not drawing water from potentially stressed sources like rivers, lakes, or underground aquifers. You're completely sidestepping the existing water infrastructure, which can be aging, leaky, or vulnerable.
And no plastic bottles.
0 plastic waste from bottled water consumption. Plus, no energy spent trucking heavy water bottles all over the place. The emissions associated with bottled water logistics are massive.
So it's a localized, self-contained system.
Right. It's inherently more sustainable in that sense.
Yeah.
Its main environmental impact is the electricity use.
But that electricity could come from renewable sources.
And that's the key synergy.
Yeah.
If you pair an AWG unit with solar panels on your roof, for example, you get truly independent, sustainable, zero carbon footprint water. That's a game changer.
Wow. Okay, so summing up, the core idea is that systems like the air fountain use established physics condensation, but apply advanced engineering for efficiency, multi-stage purification, and mineralization,
Right. To turn ambient humidity into safe, great-tasting drinking water.
giving you, the user, pure renewable water, literally from the air in your home. It means independence from the grid, potentially lower water bills in some cases, and a definitely smaller environmental footprint, especially regarding plastics and water source strain.
It really is a fascinating technology. It kind of reframes how we think about resources. It takes something ubiquitous and shared the atmosphere and transforms it directly into a private necessity, drinking water, bypassing enormous infrastructure.
Which brings us to a final thought for you, the listener. Given that this tech makes household-level water harvesting possible from basic elements around us, what else? What other essential things that we currently rely on, complex, centralized systems for things that might be scarce or vulnerable, could potentially be manufactured, synthesized, or harvested independently right at home using the basic building blocks available in our immediate environment? Think about the air, the sun, the earth right under your feet. What's the next revolution in household independence?